Swayam Prabha. Digital India. Educated India.
Is there in our breathing. It is there in the flow of blood. It is there in the analysis of sneezing and droplet transfer. In recent times, there has been a large number of works which deals with how droplets can help in spread of coronavirus and how masks can suppress the spread of coronavirus. Fluid mechanics is also important from the point of view of analyzing swimming, all the way from swimming of microorganisms to the swimming of fishes, snakes, whales, and so on. Fluid mechanics finds immense use in almost all day-to-day applications, such as electronics cooling, pumps, jets, sprinklers, just to name a few. Understanding various aspects of sports also relies on an understanding of fluid mechanics. For example, the swinging of a golf ball or the swinging of a tennis ball or a football. Who can forget the legendary free kick of Roberto Carlos? And then there is swing bowling, really understanding how air interacts with a cricket ball. After all, air is also a fluid. The entire economy can be said to depend on fluid mechanics in some way or the other. For power generation, fluid mechanics is of a pivotal importance for understanding the functioning of steam turbines, wind turbines, the process of combustion of coal, hydroelectric power plants, the dams behind the reservoirs, and so on. Our daily transport also has a great deal of fluid mechanics behind it. The complex intake of air into a car engine, the entire process of combustion inside an engine, the exhaust, jet turbines which power aeroplanes, enabling us to travel great distances which were at one point considered to be impossible, propulsion of ships, submarines, missiles, military planes, and so on. The aerodynamics of each of these objects is also a complex analysis in its own right. If you think about it, almost everything that we do is inside the atmosphere, which is again a fluid. Our life is sustained because of water, vast oceans, rivers, lakes. The scope of fluid mechanics is quite large and it has been tackled by physicists, mathematicians, and engineers over the past 100 or even 200 years. Fluid mechanics has also captured the eye of many artists, and in fact, several early descriptions of the process of turbulence, cascades, instabilities, vorticities have been captured through art. Consider these two art forms. The first one is the pouring of a jet into a pool by Leonardo da Vinci, and the second, The Starry Night by Vincent van Gogh, which shows how atmosphere is sort of forming these vortices, showing a kind of cascade. While the initial developments in fluid mechanics were based on observations and experiments, it quickly developed as an extension of continuum mechanics. A rich variety of solutions were available to various kinds of problems in fluid mechanics, and many of the closed form solutions or analytical solutions that were obtained stemmed from various simplifying assumptions. These assumptions stemmed from either simplification in geometry, such as making flat plates or axisymmetric flows, or by means of removal of effects such as viscosity. So, idealized flows, the whole gamut of complex potential flows was developed in order to tackle ideal flows. However, things are not so simple when realistic fluid flow is to be accounted for. In such cases, we appeal to solutions by means of computers. However, not all problems can be done with the aid of computational fluid dynamics. And these restrictions were in place because of memory restrictions, because of the processor speed. However, with the great leaps in computing hardware, such as developments of general purpose graphics processing units, we have now done a huge advancement in achieving high resolution, great fidelity simulations. Broadly speaking, we can classify matter as being solids, liquids, or gas. In fact, liquids and gas fall under the classification of fluids. What is the distinguishing factor behind the classification of a solid, of a liquid, or a gas? The intermolecular forces between solids are the highest, and that causes the molecules to maintain a structure so that even if a force acts on the given structure, it can at best deform. And if the force is able to overcome the intermolecular forces, then the bonds break and the solid breaks. So solids have a high intermolecular force. The intermolecular force is comparatively less in the case of fluids, by virtue of which they can flow. For liquids, it is such that it tries to maintain a certain level of adhesion between molecules, but it is not sufficient to withstand certain forces that will cause it to break very easily. In the case of gases, the intermolecular spacing is also high and the forces are also correspondingly low. In fact, in the ideal gas limit, none of the molecules interact with each other. All the molecules are going about their motion as if the other gas molecules are absent. One important property of a solid, as we've already touched upon, is its resistance to shear. Consider a solid A, B, C, D resting. Now you act on the solid by the action of a shear. Cut. Start. When we pour fluids into a container, the fluids undertake the shape of the container. This is from common intuition. Now the intermolecular forces in liquids are such that they all settle down due to gravity and they hold the shape of the container. For gases, the intermolecular forces are low, as a result of which gases tend to occupy all the volume available to them. So gases occupy all volume. Now what happens when we take a solid block like this? We hold the lower layer fixed to the ground and we apply a certain force, a certain shearing force. We know from common intuition that this particular solid will deform. I have drawn an exaggerated diagram. Typical solids such as steel, aluminium, they will not deform so large. And when you remove the force, this will come back to its original configuration. This means that solids resist shear and they come back identically to the original location if the solid is a perfectly elastic solid. In case it is not perfectly elastic, there will be some remnant of deformation even if we remove the shear force. But what about fluids? If we consider a fluid element like this, and if we act upon it by a shear force similar to the case of a solid, this particular fluid element will continuously deform up until the point the shear force is removed. It will keep on deforming. Once the shear force is removed, the fluid element will not come back to its original state. It means that fluids acted upon by shear deform. And the corollary of this is a fluid at rest has no shear. Because if we have a fluid at rest and if there is a shear in the fluid, then it means the shear will cause motion in the fluid, which means that the fluid will no longer be at rest. And therefore we have arrived at a contradiction. And this implies that a fluid at rest has no shear. Now you may ask, why shear? Because a fluid element under compression will not deform because of a certain condition called as incompressibility. The volume of this element will remain constant. It will not deform. It can, at best, change the shape while still retaining the original shape. So it will still remain like a sphere, but the radius will change. So it will not deform the object, it will only compress the object. Whether or not a substance behaves like a solid, liquid, or a gas depends on the temperature. Consider a solid which has a very tight packing. Now, as the temperature increases, the vibrational energy between the molecules begins to increase, as a result of which it can sort of break the intermolecular bonding. This leads to loosening of the bonds, and eventually the bonds loosen to such an extent that it can no longer withstand shear, and the solid starts to behave like a liquid. So you have made effectively the transition from a solid to liquid via melting. And if the temperature also keeps on increasing, the thermal energy of the molecules keeps on increasing further, as a consequence of which the energy of each molecule is so large that it can overcome any resemblance of intermolecular attraction between them. So our classification of whether an object is a solid, liquid, or a gas, it's rather subjective, and it depends on the temperature at which we are looking at it. And whether let us move on to the concept of a continuum. We know that all matter is comprised of a large number of molecules, and ideally the entire system could be described if I could tell precisely the location of each particle and the velocity of each particle. So for example, if we consider a gas, if I imagine this imaginary volume is just a volume for averaging the numbers. So if I have so many number of molecules in this particular volume, that is, I need to know the locations of all the molecules inside the box. I could then count the number of molecules. The average number of molecules would be the density of the gas. If I knew the velocities of all the molecules, then the average kinetic energy, that is the velocity squared of each molecule, is sort of proportional to the temperature, and this follows from statistical mechanics. And if this wall were to be a rigid wall, then the average number of collisions with the wall is a measure of the pressure exerted by the molecules on the wall. So effectively, it would be of great use if we knew the velocities of each particle and the locations of each particle. But how do we exactly go about finding the velocities and the locations? So consider these molecules in the system. At t equal to 0, I know the location of all the particles and I know the initial velocity. So suppose this is particle 1, 2, 3, 4, 5. So I have particle number x1 or rather x0, or just let me call it xy, and if I call the velocity component in the x direction vx and in the y direction vy. So for particle 1 I know that at t equal to 0, so this entire thing is at t equal to 0. I know that it has some location, say x1, y1, vx1, vy1. So for particle number 2 it will be x2, y2, vx2, vy2 and so on. What exactly to do with these locations? Let us consider the three molecules like this. So 1, 2 and 3. What governs the motion of this particle? We appeal to Newtonian mechanics. Which says that the mass of particle 1 times the acceleration of particle 1 in the x direction is equal to the force acting on particle 1. And this is a second order ordinary differential equation with appropriate initial conditions, so that this should be force in the x direction. So x at time 0 is x0 or x1 in this case. Y at time 0 should be y1. Vx at time 0 is vx1 and Vy at time 0 is Vy1. So these are the initial conditions. Actually, this is the x direction Newtonian equation, but we will also have the equation in the y direction. So d2 y dt2 is the acceleration in the y direction, and this will be equal to the force acting on particle 1 in the y direction. So this is in 2 dimensions the governing equation for the first particle. So now we can time step. I don't want to go into the exact details. I can perform a time stepping, meaning if the particles are located at these locations at a certain time, at the next time, depending on the velocity of this particle at this given time, it will maybe move in this direction and end up over here. So after a time delta t, it may move over here. After a time delta t, it may move over here. After a time delta t, it may move over here. So this is called as time stepping. So in order to achieve time stepping, we must first prescribe what the forces in the x and y directions are. If we consider 1, 2 and all these things as planets, what are the forces acting on planets? So force acting on 1 will be force acting on 1 because of 2, plus force acting on 1 because of 3, plus force acting on 1 because of 4, and so on. So we must account for all the planets. So this will be G m1 m2 upon R12 square in the 1-2 direction. So let me call this as E12. So planet 1 will be attracted towards planet 2. This is the direction E12 plus G M1 M3 upon R13 square E13. So it will be attracted towards this. And the sum of these two attractions is this. So instead of showing like this, if the particle initial velocity was 0, it has a net force acting in this particular direction. So at the next time step, it will arrive at this location. So you have to continue finding out the forces for all the different pairs you can do. So once you do this, we can resolve the force into its components F1x Ex plus F1y Ey, where Ex and Ey are the directions, or you could write them as I and J, doesn't matter. So this is how we obtain the force. So once we obtain the force, we can time step, find out the new location and velocity. We can again time step, but it is not so trivial to do the next time step, because like this, like the procedure we have done for particle 1, we have to repeat the same procedure for particle 2. So particle 2 itself has moved, particle 3 itself has moved. So for the next time step, we now need to evaluate again all the forces. Now, while we have considered the force calculation for planets, we can likewise do the same calculation for charged particles as well. The force for charged particles are evaluated as 1 upon 4 pi epsilon q1 q2 upon r12 square, and this is the famous Coulomb's law. In the case of molecules, all the interactions are built in a certain kind of potential. This potential is called as the Lennard-Jones Potential, and this is popularly used in molecular dynamics. Potential is given by 4 times epsilon times sigma upon r raised to 12 minus sigma upon r raised to 6. And this is sometimes referred to as the 612 potential, where epsilon and sigma are molecule dependent parameters quantifying the energy well and the width of the potential. The corresponding force is calculated as the negative of the gradient of the potential. Calculate the force on the first particle, we had to do n number of pair calculations. By pair calculations, I mean calculations like this, R12 square, R13 square, and so on. For particle 2, once again you have to do n number of pair calculations. So this will be R21 square, R23 square, R24 square, and so on. For n particles, so this will be R1n square and so on. So for n number of particles, we have to do how many calculations? We have to do a total of n square number of calculations just to find the force for all the particles in one time step. So if we consider we have 1 mole of a gas, 1 mole, which is not a very large number if you think about it, but 1 mole will contain 6.023 times 10 to the power 23 number of molecules. And for ease of calculation, let us say that the number of molecules is 10 to the power 23. Now n square calculations will mean 10 to the power 46 number of calculations, and I am not even regarding the other calculations where you have to perform additions, subtractions and such kinds of things. You have to do time stepping. Okay, I'm not even considering those. This is just for one time step. Consider a good computer which has, say, 1 teraflop per second, meaning it can do 10 to the power 12 floating point operations per second. This means that in order to do the calculation for 10 to the power 46 number of operations, we will require 10 to the power 46 divided by 10 to the power 12 seconds. This comes out to be 10 to the power 34 seconds. And if you convert this into years, you will see that it is a really large number of years. So essentially, to simulate 1 mole of a gas over one time step, you will need a huge amount of time, which is not at all feasible. So what is the way out? Instead of describing the system by averaging everything, by finding out the locations of each molecule and so on, we want to represent the discrete system as a continuous system. Instead of describing the location, velocity and all those quantities, I can directly say that this is my pressure variation, these are the pressure contours, or equivalently I can say this is my temperature variation. Okay, these are just isocontours. So I don't want to describe the system as a discrete entity, but rather I do it as a continuous system. So under what assumptions can we describe a system which is comprised of a large number of discrete entities as a continuous system? Let us begin our discussion with a gas confined in a room. And in that room, suppose we know intuitively that the density in the lower part of the room is larger than the density in the higher part of the room. So the density here, suppose it is 1100 kg per meter cube. Over here, so this is that line, this is the line for 1100, this is the line for 1000 kg per meter cube. Let us say this line represents 900 kg per meter cube. Let us say this is 800 kg per meter cube, and so on. And the characteristic length of the room is capital L. Under what conditions can we represent it as a continuous system? So let us consider a small observation window. So this is like an interrogation window. What it means is, it is a small window and I will perform all my averaging in it. And that will be sort of the basis whether we can assume it to be continuum. So we'll see how that works. So in that small interrogation window, so this is actually much smaller than what I have drawn. Suppose I have three particles, that is the distance between the particles, if I call it as lambda, so this is like the average distance between the molecules. So I'm calling it lambda. And the interrogation window size, suppose I call it as L star. So L star is not much different than lambda. L star is maybe slightly larger than lambda. So now if I want to plot the density of this particular interrogation window over time, what will I have? I will see that yes, initially there are three, so this is 3 molecules per unit volume. Now suppose one of these molecules leaves and no other molecules enter, so suddenly at the next time step I will end up with a density of 2. Now suppose 2 molecules come into the system, I will end up with a density of 4. Now suppose one more molecule comes in the system, I will have a density of 5. So each time step the variability in the observed quantity will be high. So when interrogation window is comparable to the molecular collision length scale, lambda, you may recognize lambda as the mean free path also. So mean free path defines the distance traveled by a molecule before encountering another molecule. So if the interrogation window is of the same order of magnitude of the mean free path, then there is a large variability in the density. Alternately, if I consider the interrogation window to be this large, if I sort of average the density and I plot it over time, I will see that it's more or less constant. It can change if there is a flow, so if there is remixing or the density shifts, but overall you are sort of averaging over all the different local variations. You are smothering the local variations. And this is not of particular interest to us because as engineers or physicists or mathematicians, whatever area you are working in, you ideally want to know how the density varies locally. So from 1100 it changes to 1000, it changes to 900, while I am still maintaining a field description, meaning instead of discrete particles, I am still able to say that density is a function of space. So I am losing out on a lot of information. So it can change over time, but you are losing out on information. So this is the case when interrogation window is too large. So in this particular case, the interrogation window is as large as the dimension of the room itself. Okay, so there must be some length scale which is larger than the mean free path of the molecule and much smaller than the room length scale, inside which I can sort of obtain a nice average while at the same time able to describe the local variations. I must choose the interrogation window such that it has sufficiently large number of molecules so the length scale is L star. So the volume must have sufficiently large number of molecules. The length scale must be significantly larger than the molecular length scale, but the length scale must be significantly small compared to the system length scale. Meaning, so a ramification of this statement that the length scale of interrogation must be much smaller than the system length scale is that I will capture all the local continuous variations. And the ramification of having the length scale larger than the molecular free path, mean free path or the molecular length scale is that I will not have a large variability. This means that if one molecule or two molecules exit, there is a high likelihood that two more molecules will enter. So if I plot for this kind of a length scale over time, I will see that the density is more or less constant because whatever deficit is happening, the same accumulation is also happening. So it sort of makes up. And statistically, you need a large number of molecules for this phenomenon to happen, where particles leaving, particle entering are sort of balancing each other out. So now, if we plot the measured density as a function of the volume of the cell, the interrogation cell, which is essentially delta V will be something like L star cubed. For small volumes, there will be large local variations. For very large volumes, there will be loss of local variations. So here there will be large fluctuations, here there is loss of local variations, and in the intermediate zone, you will obtain with great confidence a very constant value of density, and this is the region in which the continuum hypothesis is said to be valid. It is in this sort of interrogation volumes that the choice is made. Okay, and typically for fluids it can be as small as 10 nanometers because liquids are very closely spaced. For gases it can be as small as 100 microns, and it depends on the temperature because the mean free path will also depend on the temperature. So given a choice of the interrogation box, we can then formulate the entire problem as a continuous variable instead of having a discrete description. So like I said, for fluids it can be as small as 10 nanometers, for gases it can be 100 microns or more. So essentially we break up the system into a large number of small boxes where the box size is actually much larger than the molecular length scale, and each box sort of contains the averaging of all the properties. So instead of describing each molecule and all that, we will say that there is an average property density or temperature or pressure. We will not no more allure to the discrete nature of the system. Now the number of boxes is also so large that macroscopically you will hardly be able to look at the number of
boxes. You will hardly be able to count the number of boxes. It will be so large. So it will appear to be a continuous variable. And this is very much what happens when you look at an LCD screen. The LCD screen is actually comprised of a large number of pixels, but the number of pixels are so large that you visualize it as a continuum. So this is exactly the same analogy. Okay. So a continuum hypothesis it helps us in formulating problems involving continuous media. So it can involve problems of solid mechanics and it can involve problems of fluid mechanics, and it will help us to describe them in terms of fields such as pressure. It can be function of x, y and z and time. Fields such as temperature, it can be a function of x, y and z and time. So they are no longer described by averaging molecular motions. We sort of lose out on that molecular level information and we average out everything and we say that in our domain everything is a smooth continuous variable. And this allows us to do a great deal of mathematical manipulations which are otherwise almost impossible to do in the case of discrete nature of particles. But can we always neglect the discrete nature of particles? We come to the concept of Knutson number. It's defined as the ratio of the mean free path to the system length scale. So let me draw a system like this. Suppose this is a channel, okay, and the distance is L. Now suppose we have a high temperature, and a high temperature means the mean free path is quite large. The particle will travel a large distance before colliding with another molecule. Okay. In that case, the molecule before striking the wall is more likely let us consider a channel like this. So if the mean free path is something like this, if the mean free path is smaller than the channel size, then we can say that the flow is sort of trying to lie in a continuum regime. So if the mean free path is comparable to the system length scale, then the molecule will interact equally with the walls of the channel as it is likely to interact with the molecule. If the mean free path is larger than the system length scale, it means that it will definitely strike the wall before striking another molecule. So physics wise, if lambda is much larger than the system length scale, it means that the molecule necessarily collides with walls. So molecule, instead of interacting with other molecules, is interacting more with the walls. And this means that the physics has to necessarily account for the discrete nature. These kind of flows are called as free molecular flows. In such kinds of flows, you necessarily have to account for the discrete nature of the particle. If the mean free path is much smaller than the length scale, this again brings us back to the same set of assumptions behind the continuum hypothesis, and these are continuum flows. Physically, it means that there is a large number of molecules and a molecule strikes another molecule before it strikes the wall of the container. So it behaves like a continuum flow. Where can we see free molecular flows? So vacuum systems, which are used extensively in semiconductor industry. So analysis there depends on free molecular flows. Re-entry vehicles, when a spacecraft is making a re-entry from space, the density of space is quite less, So there are very few molecules to strike the object. Okay, so in this case, the analysis has to be done as a free molecular flow.
The idea of the Knutson number is not just restricted to the idea of fluids. It can in fact be extended to several other non-fluid phenomena as well. Consider a huge collection or crowd of people. The people are not able to move a large distance before they collide with each other. That is, they are very densely crowded. And you can see this in crowded railway stations or crowded sporting events. And the collective motions of such kinds of crowds leads to the macroscopic observation which resembles that of a fluid. In this case, it is a Mexican wave, which you might have seen in football stadiums or cricket stadiums. Similarly, these ideas can also be extended towards analyzing granular flows, where instead of having fluid particles, you have actual discrete particles, but they are so small and numerous in numbers that the macroscopic manifestation of their physics can be somewhat described by means of fluid mechanics. The demarcation between solids and fluids is rather blurry when you think about the various timescales present in the problem. There is a very famous experiment in which pitch or very highly viscous tar is held inside a funnel and it is allowed to drip. It drips over a time of 13 years, meaning if you stand and look at the experiment for days or even months or even a year or so, you will hardly see any movement. It will almost appear as if the entire drop is like a solid. Over 13 years, the drop pinches off and falls into the beaker, which is held below. Over geological timescales, rocks are also said to flow, and we can see this when we observe the various patterns that we find when we dig up rock samples and rock cores. Now again, we can assume that the rock is an idealized, generalized fluid with a very high viscosity, and in order to break the bond, the intermolecular forces between the molecules of a solid, we have to overcome an activation energy. When the activation energy is quite large, it is difficult to break the bonds and induce a flow in the rock. However, an increase in temperature and pressure does give rise to a weakening of the activation energy relative to K times T. So the factor K times T comes in from statistical physics. So increase in temperature and pressure leads to flow of the rocks. Let us imagine that the stratification in the ground is as shown. There are multiple layers of rocks, and when pressure acts in this direction, there is a deformation of the layers, And this we can often see in as various spectacular rock formations. And this has a certain analogy with the stirring or the stretching and folding of the milk when we pour it over black coffee. So you might have seen in various cafes that they make a nice pattern on top of the coffee. So that particular stretching and folding event and takes around 10 seconds, and we know for a fact that it is a fluid. And a similar looking phenomenon happens in geology, but that takes thousands of years. So the time scale is also an important factor in order for us to assess whether a substance is a fluid or a solid. With this, we come to a closing of this particular video. In this video, we have seen the distinction between solids and fluids. We have seen how temperature can cause a transition of phases from solid, liquid to gas. We have seen the ability of solids to withstand shear, but liquids cannot withstand shear, they continuously deform. We also touched upon the important fact that solids, when they are not perfectly elastic, will also have a sort of remnant or a permanent deformation. We have studied the continuum hypothesis, in which we have analyzed how we can abstract the molecular motions and molecular information to a field continuous variable. And this field continuous variable representation will help us in mathematically simplifying various problems. Lastly, we have seen how solids can sort of behave like fluids over extremely long time scales. And it is not just the physical intuition that we have that classifies a substance as a solid. So with this, we close this video, and I'll be back with a new video next time. Goodbye from me. Bye.